Okay, so now I'm going to do a whole bunch of mole ratio problems, a whole bunch, so that you can really get a handle on these. They're super important for stoichiometry, for understanding stoichiometry. Okay? Each problem I'm going to do it two ways. First, I'm going to treat the equation, the chemical equation, kind of like a recipe, all right, where we've got our ingredients and then we've got the stuff we're baking. This method really makes sense. Like, you'll understand what you're doing, but it requires a little bit of thought. Then I'll solve each problem using a conversion factor method. The conversion factor method doesn't require any thought, but it doesn't make any sense. So it's really easy to get in the habit of only using the conversion factors, running through the math, but having absolutely no idea what you're actually doing or why you're doing it. Okay, so that's why I'm going to do each of these problems two different ways. Okay, so let's get started. Here is the first equation I'm going to be working with. 2 moles of H2O, water, makes 2 moles of hydrogen gas and oxygen here. If there's no coefficient in front of the oxygen, in front of one of these chemicals, we know that it's really 1, that it means 1 mole. So hey, if it helps you, go ahead and write that 1 in. There's our equation. Here is the question. How many moles of O2, of oxygen, will be produced from 6.2 moles of water? Okay? So, first of all, I want you to think of this like a recipe. And right now, it's saying that we start with 2 moles of this, and that gives us 2 moles of this and 1 mole of this. But we're not talking about starting with 2 moles of H2O. We're talking about starting with 6.2 moles of H2O, okay? So this is just like when you're cooking and you've got to double or triple or quadruple a recipe. What do we have to do to this recipe so that instead of starting with 2 moles of water, we start with 6.2 moles of water, okay? We have to multiply everything in this equation by something that's going to get us 6.2 moles of water. We can figure this out a couple ways. First thing that I can do is I can do 6.2, which is this, divided by 2, which is that, and that gives me 3.1. Okay? That like gives me the factor. And what I mean by that is that we take each one of these numbers and we multiply it times 3.1. 2 times 3.1, and now we get 6.2 moles of this, okay? So now we're starting with 6.2 instead of 2. We multiply this by 3.1. Now, we'll also want to multiply the number of H2 times 3.1. So now we're getting 6.2 moles of H2. And we'll want to take this number, which is 1 times 3.1, multiply it there, and we get 3.1 moles of O2. So once again, we treat this like a recipe in the kitchen that we're doubling or tripling. Instead of multiplying by 2 or by 3 or by 4, we multiply everything in this recipe by 3.1, and we get 6.2 here, so that's what we're starting with. Then we get 6.2 moles of H2, and we get 3.1 moles of O2. And that kind of makes sense, right? Because there's this 2-to-1 ratio of water to oxygen. We start with 2 of these, we get 1 of these. So this is half of what we have here. Okay? So if we start with 6.2, we multiply everything by 3.1, and we get 6.2 here, and this 3.1 is half of what we had over here. Okay? So that's how we can do this equation, treating it like a recipe in the kitchen. Now let's look at how we can do this using conversion factors. Okay? What we're going to do is we're going to start with 6.2 moles of H2O. Now what I want to do is I want to write a conversion factor that tells me the relationship between the moles of water and the moles of oxygen. Okay? We can sum it up with this. It tells us for every 2 moles of H2O, I get 1 mole of O2. 2 here, 1 here. Okay? We get this relationship. And what I can do is I can use this to write a conversion factor. There are 2 different conversion factors that I can get from this. I can write 2 moles of H2O over 1 mole of O2. Okay, that's 1. Or I can flip it. I can do 1 mole of O2 over 2 moles of H2O. And of course, I'm just getting the numbers from the chemical equation here, 2 and 1. So I've got these two conversion factors that are flips. I could use either one of them. They're both equally good. The one that I want to choose, though, is the one that I can multiply by this and cancel out moles of H2O. Okay? That's going to be the one that has H2O on the bottom, because it's on the top over here. So I'm not going to use this one. I am going to use this one. I'm going to multiply it here. And now I have H2O on the top, H2O on the bottom. So they cancel out. And when I do this math, I'm going to do 6.2 times 1 divided by 2 equals 3.1 moles of O2. And check it out. I use a conversion factor method and I get the exact same answer that I got when I use this like a recipe. Okay? So the recipe or the conversion factor both give the same number. Okay? Let's go on to the next one. Okay, so how many moles of H2O will be required to make 19.2 moles of O2? Let's treat this like a recipe first, okay? Right now this is a recipe for 1 mole of O2. What are we going to have to do to this recipe? Double it, triple it, quadruple it is what I mean. What are we going to have to do to this recipe to make it a recipe for 19.2 moles of O2? Well, there's a 1 right here. 1 mole of O2 in the recipe. So it shouldn't come as a shock that we have to multiply the recipe by 19.2. And now if we multiply it by 19.2, it will become a recipe for 19.2 O2 times 19.2, and this is going to give me 38.4 moles of H2. Multiply this by 19.2, because just like when you're cooking, right, you got to multiply everything in the recipe by the same number. And this is going to give us 38.4 moles of H2O. This is what happens to the recipe when we size it up to cook for 19.2 moles of O2. So the answer is, how many moles of H2O are we going to need? We're going to need 38.4 moles of H2O. That's the recipe method. Okay? Now let's look at the conversion factor method. Just as before, we realized that the relationship between water and oxygen by using the chemical equation here is 2 of these to 1 to these. So we can get these 2 conversion factors. We have 1 mole of O2 to 2 moles of H2O, or 2 moles of H2O to 1 mole of O2. I'm going to start here with 19.2 moles of O2, and I want to be able to multiply this by the conversion factor that's going to cancel out my moles of O2. So I'm going to choose this one here because it has moles of O2 on the bottom. Cancel out, cancel out. I do 19.2 times 2 divided by 1 equals 38.4 moles of H2O. I know it's moles of H2O because that's the unit that I have remaining. Okay? So sometimes people ask, why are you doing it both ways? Why are you doing it the recipe way and then the conversion factor way? Okay? The reason is because, for me, the recipe way makes a lot more sense. But teachers and textbooks are in love with conversion factors. They love them. They can't get enough. I don't think that conversion factors make any sense at all. All right? But just because they're like commonly used, your teacher's going to ask you to do it, your textbook's going to ask you to do it, that's why I'm doing them too. But what I want you to focus on is actually why we're doing it, the way we multiply things and get the answers here with pretending it's a recipe. I want you to focus on this so that you understand what's going on. And as you can always see, the answer that we get from the conversion factor method is the same as the answer that we get when we're treating it like a recipe and multiplying everything by some number. Okay? All right, let's move on to the next question. So, 2 moles of H2S, hydrogen sulfide, combined with 3 moles of O2, oxygen, to make 2 moles of SO2 and 2 moles of H2O. Using this equation, we're asked how many moles of O2 are needed to combine with 8.4 moles of H2S. Okay? What do we have to do with our recipe to cook with 8.4 moles of H2S instead of 2 moles of H2S? What we're going to want to do is we're going to multiply this by some number that's going to give us 8.4. How can we figure out what that is? Well, you might sort of be able to do it in your head. Or you can do 8.4 divided by 2, and that's going to give us 4.2. So 4.2 is the number that we're going to have to multiply everything by so that we can move from 2 moles of this to a recipe that uses 8.4 moles of this. Okay, so everything we're going to multiply it by 4.2. Okay, so here we have 3 times 4.2, and that's going to give us 12.6 moles of O2. 2 to 3, 8.4 to 12.6. All right, let's see how we can do this using conversion factors. We'll start with 8.4 moles of H2S and multiply that by one of these two conversion factors. These conversion factors are just telling us the relationship that we have here of 2 moles of H2S to 3 moles of O2. And I can use this relationship to make these two conversion factors. Which one do I want to use? I want to use the one that has H2S on the bottom so that it cancels out. So I choose this one. Cancels out, and this is going to give me, what a shocker, 12.6 moles of O2. Why moles of O2? Because it's the unit that's left here. Okay, that's how we can do it, treating it like a recipe. Here's how we can do it using the conversion factor. Here's the next mole ratio problem. Look, maybe you're getting the hang of these. Maybe you feel great. Turn the video off then and move on to the next thing. But if you'd still like some more practice, hey, let's party all night long with mole ratio problems. We'll keep doing them until it feels really comfortable and you're sure that you could do any question that's thrown at you. Okay, starting with 9.2 moles of O2, how many moles of H2S will you need, and how many moles of SO2 will you get? Okay, so starting with 9.2 moles of O2, right now our equation is written to start with 3 moles of O2. So what are we going to have to do? We have to find out how to double, triple, quadruple, whatever we want to do to this to get it up from 3 moles of O2 to 9.2 moles of O2. What am I going to have to multiply it by to turn this 3 into a 9.2? I can figure that out by doing 9.2 divided by 3, and I'm going to get 3.1. So 3 times 3.1 is going to give me 9.2. I'm kind of rounding here, all right? If you do the math, it's not exactly right. Okay, anyway, times 3.1 is going to give me 9.2 moles of O2. And how many moles of H2S am I going to need? Well, I'm going to have to multiply everything in the equation by the same amount. So times 3.1 here is going to give me 6.2 moles of H2S. So that's how much H2S I'm going to need to combine with my 9.2 moles of O2. And then, how many moles of SO2 will I get? I take my 2 moles of SO2 and I multiply that by 3.1 as well. I've got to do the same thing to the whole equation, and then I get 6.2 moles of SO2. So that's how we do that. Let's look at how we do the conversion factors. You guys are really probably getting the hang of this now, so I'm not going to show all of the conversion factor steps. We start with 9.2 moles of O2 times, what is our relationship between O2 and H2S? We have 3 moles of O2 to 2 moles of H2S. So I want to write that as a conversion factor with O2 on the bottom so that it cancels out. So 3 moles of O2 to 2 moles of H2S. Moles of oxygen up here cancel out, moles of oxygen down there cancel out. And I get the same answer that I got here. I get 9.2 moles of H2S. And now let's just show how we can do this with the moles of SO2. it's going to be the exact same thing. I'm not even going to like get rid of this thing that's all canceled out here. I'm going to multiply it by an equation that shows a conversion factor that relates oxygen here and SO2 here. Okay, so again, 3 moles of this to 2 moles of this. So 3 moles O2 goes on the bottom, and 2 moles SO2 goes on the top. Cancel this out already. This is canceled out. And I'm going to get, after I do the math, 9.2 times 2 divided by 3 equals 6.2 moles of SO2. Sometimes I write moles with an E, sometimes MOL, because sometimes I get lazy. Okay, so that's that. Let's do 2 more. If this feels good, turn it off and move on. So here we have an equation that talks about propane burning, which is C3H8. Nothing in front of this, so we can put a 1 here. 1 mole of this plus 5 moles of O2 gives me 3 moles of CO2 and 4 moles of H2O. My question here asks me how many moles of oxygen are needed to react with 7.2 moles of propane. What do we have to do to this equation to size it up so that we're starting with 7.2 moles of propane? Right now we're starting with 1 mole of propane, okay? So this isn't the hardest thing in the world. We're going to have to multiply this whole equation times 7.2, and that's going to give us 7.2 moles of propane. How many moles of oxygen are needed? Well, we have to multiply it by 7.2 as well, and that math is going to give me 36.0 moles of O2. Let's look at the conversion factor method. We're going to start with 7.2 moles of C3H8, and we're going to multiply that by a conversion factor that says 1 mole of C3H8 to 5 moles of O2, which is going to be on the top, which is going to be on the bottom. This is on the top, so we want this in the conversion factor to be on the bottom. So I'm going to say 1 mole, I'm getting it from right here, 1 mole C3H8 below 5 moles of O2. This cancels out, it's on top. This cancels out, it's on the bottom. And it gives us 7.2 times 5 divided by 1 equals 36.0 moles of oxygen. Okay? 1 more. Our last one. How many moles of propane are needed to make 13.5 moles of CO2? In order to do that, how much O2 will be needed? Okay? What do we have to do to our equation right now in order to make it 13.5 moles of CO2 instead of 3 moles of CO2? We're going to have to multiply it by some number that's going to move it from 3 up to 13.5. And what I can do is I can do 13.5 divided by 3, and that's going to give me 4.5. So I can multiply this by 4.5, and that'll turn my 3 into a 13.5 moles of CO2. So then when I'm talking about how many moles of propane am I going to need, I multiply it by the same amount, and I get 1 times 4.5, 4.5 moles of C3H5. And then I'm asked how much O2 am I going to need? Well, I have to do the same thing to all the pieces of my recipe. So 5 times 4.5 is going to give me 22.5 moles of O2. This is what happens to my recipe when I increase the size of it. Let me just show you these really quickly. I'll start with 13.5 moles of CO2 times a conversion factor that talks about the relationship between propane, C3H8, and CO2 here. CO2 is going to be on the bottom so that it cancels out. So 3 moles of CO2 on the bottom, 1 mole of C3H8 on the top. 13.5 times 1 divided by 3 is going to give me 4.5 moles of C3H8. The number is the same, even though the process is different. Oh, what did I forget to do? I forgot to cancel these out. Or I could, I'm not going to get rid of it, I'm going to just keep it there. Or to find out how much O2 I'm going to need, Well, what is a relationship between CO2 and O2? It's 3 to 5. So 3 moles CO2 on the bottom and 5 moles of O2 on the top. These cancel out. 13.5 times 5 divided by 3 equals 22.5 moles O2. The same answer regardless of whether I do it the recipe method or the conversion factor method. If you made it all the way to this end of this video, you partied with me all night long on mole ratios, you're a rock star. But more than anything, I bet this really makes sense, and I bet you can tackle any mole ratio problem that's thrown at you. Feel free to use the recipe method or the conversion factor method unless your teacher says that you have to use a conversion factor method, then go ahead and use it, but know in the back of your mind what is actually going on and why you're multiplying by what you're doing and all that sort of stuff. All right, good luck.